Well, today, if you looked at the screen before, you know that chemistry is the science that studies matter and its properties and reactions. That's what we're going to talk about today. We're going to talk about properties of materials, then we're going to show you some demonstrations to illustrate these properties, and then we're going to do some chemical reactions. We're going to do two very general kinds of chemistry, acid-base reactions and oxidation-reduction reactions. This experiment again involves carbon dioxide, but we're going to use, we don't want to bring in a big cylinder of carbon dioxide gas, so we're going to use dry ice, which again is just a solid form of it. So what I have, I'm going to put in this flask some water, but I made the water a little basic. I added a base for the purpose of this experiment. Now what I want to try and convince you of is that when carbon dioxide reacts with water, the water becomes more acidic, because carbon dioxide and water gives carbonic acid. But the problem is you're not going to be able to see by looking at it. It doesn't change color. So how are we going to convince you that when you add carbon dioxide to water, it becomes more basic? More acidic. I put a little base in there so you'll see the color change. But what we're going to do, so you can see the change in pH or the change in acidity, I'm going to add an indicator. An indicator, just as its name applies, is an organic compound that changes color depending on what the pH is. So this is the color when it's very acidic. And what's going to happen when we add dry ice to it? Maybe I should put it in.
Did you already do the glow one?
Which one?
The glow one where it flashes.
Carbon dioxide absorbs infrared radiation, so it makes the atmosphere hotter. And the other one is acid rain.
Okay, that is 0. It's negative 12, negative 13. So it took so much heat that the water on the cardboard got frozen, and now I will try to lift it. And the cardboard is attached because the water freezes. You see? All right, so that's the...
Let me just throw in one quick one before you. Who can guess what this white solid is? Something you all know. It's just table salt. Oh, No, but you're warm, but you've got half of it right. It's got sodium in it. It's not sodium carbonate.
Salt.
Salt, you know what the formula for salt is? NaCl. Now, as I say, you really are chemists already. Who can tell me 4 properties of salt? And some of them are very obvious. Yes?
Well, salt usually goes on meals.
It goes on meals. It's really not very good for you. It's a solid. What's even more obvious than it's a solid? What's the first thing you notice about it? It's white. It's white. So white, solid. If you ever help your mother cook, your father cook, you know another property. What's the another property? I didn't do that. Exactly. Soluble in what?
Water.
It's soluble in water. And the other one you may not have thought of, but when you think about it, it's really obvious. So it's a solid, it's white, it's soluble in water, and it's stable in air. Some materials, you take them out in air, they catch on fire. It's called pyrophoric. So you know 4 properties already. Now let's take another common material, sand, SiO2. We'll put some of that in another test. Now this is after purity, white. Sand, you get some other impurities. Formula for sand is SiO2. Who knows the properties of sand? Or say that it should be white and it's a solid. What's another property? Remember what we said about sodium chloride? I'll give you a hint. Remember what we said about sodium chloride? If you've ever sat on the beach, you know this property. What is it? It's not soluble in water. Because if sand was soluble in water, if you sat on the beach, waves and the beach would disappear. And also it stayed within. So properties are very important because if a chemist runs a chemical reaction, let's say compound 1 and compound 2, and mixes them up and they get a reaction to get compound 3, that would be wonderful. That's not the way it works. Usually you get mostly the product you want, but you get small amounts of other materials that you have to get rid of. So you have to know the properties. That's especially important, for example, in pharmaceuticals. You wouldn't want to use some medication that had 0.1% of something that was very toxic. So you have to know the properties of materials to be able to purify it. So who can tell me if you mix these 2 up? You mixed up 2 compounds, then we have a mixture. How would we separate that? Who can tell me how we would separate that?
Add water and then
That's
probably
right.
flow.
Add water in a filter, the sodium chloride would dissolve, and the sand would be on the filter paper. Now let's add another material to our mixture. Remember the definition of a mixture is that it can be separated by physical means. So let's I'm going to add some iron to this mix. Now we have 3 components in this. And how can we separate the iron from these other 2 materials? What's the property of iron? Magnet, very good. This just shows that that really works. So if you had this mixture, the first thing you probably do is take a magnet and pull up, actually pour it out. You can see you can pull up the iron. You would dump that out, and then as this young man said, after you remove the iron, you add water and filter it. So you had a mixture of 3 components that using the physical properties of solubility and magnetism, you can separate all 3. Now there's another interesting property of some materials. I hope you remember this word when you leave. Sublimation. Does anybody know what sublimation is? Sublimation is the property in which a material goes from a solid state to gas without going through an intermediate liquid phase. So for example, you have an ice cube, you put it on the table, it melts, you get a liquid. Go back a week later, what would be on the table? Nothing, because it's evaporated into gas. So it went from a solid to a liquid to a gas. This is the way most things operate. Alexey, can you demonstrate? What we're going to do is heat this, and you'll see the property of sublimation. Iodine has the formula, well, chemical element is I for iodine, but it's actually a molecule. And you can start to see some purple vapor coming up. And it's cool on the top of above in the test tube, that will actually condense out, into the side of the test tube. We're going to see another material that has the property of sublimation in a minute. Compound has this property. This is still hot, but after the show, if you want to come up and you'll see that some of the crystals have actually sublimed up and they're sticking to the wall. Now I said there's another material that has the property of sublimation. Can anybody guess what it is? I'll show it to you and see if you know what it is. Does anybody know what this is? It's dry ice, which is just solid carbon dioxide. So what we're going to do is put some in this test tube. And I hope I can convince you that it really does sublime. To prove that, I'm going to attach a balloon to this test tube. So this is evidence that carbon dioxide sublimes because we have the solid in the test tube. And at room temperature, it's starting to give off CO2 gas. So it's converting from a solid, it's not melting. If I put an ice cube in there, attach a balloon, nothing would happen to the balloon. It would just melt to a liquid. So this carbon dioxide has the property of subliming. Now another important property is density. Density is the mass per unit volume. So for example, if you throw a penny and a cork in the swimming pool, which one floats? Cork. The penny is smaller, but it would get a large cork. The penny is smaller, but it would actually sink because it has a higher density, it has a higher mass per unit volume. So who can guess what's in this balloon? Helium. Why didn't you say that? Say that again. Helium. Helium is less dense than air. You want to bet me on that? Okay, I'll bet you $1,000. Helium, the young man said helium is less dense than air. So let's see if he's right. Alexey, can you? I'm waiting at the one to print this.
Oh, okay. So I can help you with this.
I don't know which. You pour this initially.
Oh, wait a second. Nothing without
I can see my $1,000 now. Maybe I'll go to St. Bart's for the weekend.
You need this.
Okay. This experiment also proves why if you're a chemist or a scientist, you also need to be a little bit of a lawyer. You have to be careful what you say.
Oh, wait a second. Can I just first?
You have to pour some more in the cup. Incidentally, this is liquid nitrogen.
I'd like to put the glove on. No bare hands. We'll be in trouble.
Incidentally, I'll take a check. But I'll let you call, as the defense attorney would say, would you like to qualify your testimony? You have to call. You said helium is less dense than air. What do you have to, how do you qualify?
Just wait and it will come out. Just wait. It is. It is. Oh, okay.
So you're right. You're right, you have to qualify. Helium is less dense than air. Oh, you have to ask that. At room temperature. Many properties are dependent on temperature. Like water. Is water always a liquid? No. You put it in the freezer, it goes to solid. You put it in a pot and boil it, it goes to a vapor. So carbon dioxide, helium has the property of...
Who wants to participate in that kind of experiment?
Yeah, we need everybody.
Anyone
to
below,
pass it. Anyone below.
All right, so the next experiment is ice floating in the water. What could be simple? But I want you to guess. Is it going to float or is it going to sink? I have a piece of ice. What do you think? And let's try. I'm going to put ice, and what is it doing? It's floating. That's a regular piece of ice, and it's floating. No problem, no doubt. How about this experiment? That's just another piece of ice. And I'm going to put it in the water. But that's not a regular ice. The next one is made out of G2O. G is an isotope of hydrogen. So what that one is going to do, let's just watch. And then just sit. Oh, it sits to the water. It's not floating. This kind of water is called heavy water. And that is a heavy ice. By the way, on one of the planets, there's a liquid ocean of liquid ammonia. Now, the ammonia ice is more dense than the liquid ammonia. What's going to happen with that? In the winter time, when it freezes, the ice of liquid ammonia goes to the bottom because it's heavier. So we're kind of lucky on our planet that the water, the ice made out of water, it's floating on surface. Well, you need a hydrogen deuterium, but it's the tritium isotope that is used in atomic bombs. Okay? All right, so when you're ready, bring your balloon. Do not inflate it too much because we're going to put it in the liquid nitrogen and see what happens with it. It has to fit into this box. That would be much faster. All right, so please bring your balloon in here or give it to the assistants and I will collect it from you. All right, good. I'll take it from you and just let's put it there. Anyone else? Small size balloon. All right, thank you. Oh, wonderful. I'll take your balloon. Thank you. Still waiting for this one to shrink. you. Just put it in the table, on the table. Good.
And you put it on the table too.
Yeah, put it on the table. Thank you. Thank you. Perfect. We need someone to count. How many balloons are there? It's already 3, and then this is 4, number 4.
Yeah.
That.
I think I'm going to have to put some more liquid nitrogen.
Thank you, thank you, thank you. Oops, oops, sorry. All right, thank you.
Carbon dioxide blew it up in the burst.
Do we have any other balloons?
No. I'm not going to give it another shot. Liquid nitrogen.
No, this is enough.
That's enough?
This is enough. That's a lot of it.
And what Professor Ignatchenko is showing you is a demonstration of what we call Charles' law, which says that the volume of a gas is directly proportional to the temperature. So if you decrease the temperature, you decrease the volume. And if you increase the temperature, you increase the volume. So what do we do here? We decrease the temperature significantly so the balloon volume shrunk. Now he's going to put it on, throw it on the floor. It will come to room temperature, so the temperature will increase, and what will happen to the volume of the balloon?
Okay, we'll see how many are there in that box. But okay, I am gonna put this on the floor. Do not step on it because liquid nitrogen is dangerous and no one is around.
So again, what you're seeing here is a demonstration of Charles' law. The volume of a gas is directly proportional to the temperature. So the balloons are coming to room temperature and they're coming back to their original volume.
Okay, we're gonna do our next experiment, and I want you to guess how many pieces of styrofoam chips can I put in this beaker? That's right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I got 12. Is that all? Can someone guess how many can be there? The styrofoam chips made out of the air and plastic. There's a lot of air inside. I'm going to release that air. Let's just see what's going to happen if I spray this with acetone. Acetone dissolves styrofoam and they kind of shrink. Do you want to take another guess and see how many I can place in this beaker? Alright, let's just put all that. packaging material can be recycled. After the use, it can be dissolved in the solvent and reprocessed again. In the process of this styrofoam, the air is bubbled through the solution, and it's pulverized and taken out the same way as a cotton candy is made. The cotton candy is made the same way. It's a sugar that is the air bubbles through that, and it dries quick. Now, what you can do at home, put the cotton candy bowl in a bowl of hot tea, and we'll drink. You will get a sweet tea. Alright, so I can continue, and I can put the entire box in this little bowl.
Do that. Anybody have an idea? No, I'm not going to take it. I need something colder than dry ice, which would be what? Ah, and then here I have liquid nitrogen. So the gas is condensing back into the test tube because I put the test tube in liquid nitrogen. And the only thing colder than liquid nitrogen, well, the main one is liquid helium. So is this a chemical reaction? Who thinks it's a chemical reaction? Who thinks it's a physical change? That's what it is. It's still carbon dioxide. I converted it from the gas to the solid, but I didn't do any chemical change. It's still CO2. All I did was change the temperature to get it to be a gas or a solid.
All right, now we move into the acid-base reaction. The next one is called rainbow reaction. Rainbow colors. So now we're going to mix all the colors together and put them in one beaker. Let's see what happens. Chemistry is an experimentation. We always want to see by the experiment. Now, I'm going to do another experiment that is changing the colors. Colors change. How can we turn it back? Should we add something? Now, what color do you want? Who wants yellow? Okay, who wants green? And who wants red? Peach. try that again. And with the magic spell, maybe it will be faster. Alright, let's turn it blue again. That blue? Alright, now let's turn back to the colors. Green, yellow, and what, that pink? Okay, so should we say 1, 2, 3, and then maybe it will change. Green and pink. Okay, 1. That's pink. Well, this is still frozen. Okay, what other colors do we want? This is still blue. Green? Okay, let's do green. Now the next one is called pulsating light. So it's going to produce a little bit of light. But the interesting thing is that this light is not going to stay all the time. It will be pulsating. And let me just count. In every 2 minutes, it will produce light, a pulse of light. Right, so let's keep an eye on this, and in like 1 minute and a half, roughly, it should be pulsating. But, so the whole force is flashing with the light. Very beautiful. Now it's coming. And it's gone. Same way as the lining box. So in about 1 minute, it will do it again. Right, it's about ready to flash the light again. Oh. Start timing this and you will see how many seconds does it take between the flashes. Now we're gonna do the next experiment. It's called blue bottle. The color will again disappear if you shake it, and then will come back again by itself.
Now, this is an example of one of the most common kinds of reactions in chemistry, an oxidation reduction reaction. Well, one that you're familiar with is iron. If you have a car or a fence and it's made of iron, if you don't paint it and keep it preserved, what happens? It rusts. And after years, it would just disintegrate into a pile of rust. But an interesting fact, if you have an aluminum ladder, that's very stable. But aluminum is actually much more reactive with oxygen in the air than iron. So why is an aluminum ladder stable for years, but a piece of iron will rust? Who has an answer? Well, the answer is that even though aluminum is much more reactive than iron, it forms an oxide on the surface, and the oxide is impermeable to oxygen from the air. So even though it's more reactive, you can't have a reaction unless the two reagents, the two materials can get together. So iron forms a very porous oxide. It just peels off, and after a year or so, your fence would turn into a pile of iron oxide rust. But the aluminum ladder is stable because the iron forms a very stable oxide on the surface. And the oxygen can't get through it to get to more aluminum underneath. So what I'm going to do here is put some water that I've made basic with a sodium hydroxide. And to it, I'm going to add glucose. Glucose is just a common sugar, but it has the property of being a reducing agent. And if you study chemistry, you'll know what that is, or you will study chemistry, you'll find out what a reducing agent is. I'm just going to shake it up a little bit so it dissolves. And now I'm going to add a couple drops of an indicator methylene blue. And the methylene blue is going to react with the glucose. It's going to be reduced by the glucose. I'm afraid this was not going to work so well. I think I put too much methylene blue in it. Now let's do another kind of oxidation reduction reaction with metals. I have here a solution of cupric chloride, a salt of copper. And what I want to demonstrate in this experiment is if we react two materials, it can depend on the particle size of the reactant. The smaller the particle is, the more vigorous the reaction. So I have copper here, copper salt, and I don't have a strip of zinc, so I have a galvanized nail which has zinc on the surface. And you see when I put the zinc in, nothing much happens, because it's a very bulky, solid piece of zinc. But in this bottle I have some zinc. It's a very fine powder. Let's see what happens when I add that. Let's add a little more of this. You see, when I add the fine powder, it reacts very quickly. And zinc metal is deposited. So the point I want to make is, as I said, when you react two materials, the smaller the particles of the reactants, the faster it goes and the more heat it gives you. gives off. So think about this. If I say the smaller the particles when you react, and I want to get to the limit of what's the limit of decreasing the particle size of material, what do you get? In other words, this spatula is a piece of metal. If I keep dividing it, I finally get what? The atoms or molecules. An example of that is in your car. The car goes because you have a vapor phase reaction between molecules of oxygen and gasoline in the car. So the vapor, oxygen comes into the cylinder of your car, gasoline comes in, the spark plug puts a spark across the gaps of the spark plug, and you get an explosion and drives your car. We're going to mimic that, but instead of gasoline, we're going to use methanol. Instead of a spark plug, I'm going to use 2 nails. I have here a 1 liter polyethylene bottle. And what I'm going to do is put 2 nails that almost touch. So the polyethylene bottle will be the cylinder of your car, the 2 nails will be the spark plug. I have to get the 2 nails so they're almost touching. Now, if I say the bottle is empty, that's really not correct. What's in the bottle? Air, right. Air is a molecule, is a mixture of oxygen and nitrogen. So what I'm going to do now is I have everything ready to go, but I need my fuel. I'm going to use methanol, methyl alcohol. So I'm going to pour some liquid methanol in. But of course, if I put a spark across there now, I'd be blown to bits because we have vapor and liquid. So what we need to do is, what we're going to do is shake it up, fill up this bottle with the vapor. Now is a bottle that's filled with methanol vapor and air, but the critical reaction is methanol and oxygen. And I have a Tesla coil, I'm going to put a spark across it and we'll see what happens. Again, we're at the limit of particle size with molecules. It blows up because we had a vapor reaction with oxygen, we get CO2 and water, but the temperature is very high, so it expands and glows everything else. So I want you to leave thinking that all oxidation reduction reactions are violent. We're going to do one that's very benign. This is a reaction the way they make mirrors. A mirror is just a piece of glass that has a very reflective thin layer of silver on it. We're going to try and mimic that in this flask. And again, we're going to use our favorite reducing agent, glucose. And in this bottle, I have some silver nitrate. We're going to put silver nitrate is going to be reduced by the glucose, and if we're lucky, we'll get a nice reflective mirror. We'll put about 125 milliliters of this solution in. About 25 milliliters of glucose solution in. Because if you get silver nitrate on your hands, it will be reduced by the proteins in your skin. You'll get silver metal, a black mark on your skin. And of course, you can get it off if you want to put your hand in concentrated nitric acid, but I prefer not to do that. Now, this is not a clean reaction. You see, it's starting to give silver metal. So what it does, it forms silver metal in the solution, a dispersion of fine particles But if the bottle is clean, I hope I cleaned it well enough, eventually you'll get some of the silver will actually form a mirror on the surface of the glass. Now, Professor Ignatchenko is holding a heat gun because we know in chemistry, whenever you heat a reaction up, it goes faster. So if we want this to speed up a bit, we can heat it.
By the way, by this process, Christmas decorations can be prepared. You can put this solution inside of any glass bowl and it will be covered by the silver.
This is what's called an auto-catalytic reaction. When you pour the silver on the surface, then it goes faster. The silver catalyzes towards the reaction.
Alright, we got coming to the end to our final experiment, fireworks. Alright, so this is the explosions. One balloon is filled with helium. We're gonna just burn and see what happens. It's not a flammable gas, so it's not that dangerous. Alright, that's how loud it is. Now, the next one is filled with hydrogen, and we have an expert on explosions, Jordan Kostera, and he's going to do that little balloon. So be prepared, it's going to be very, very loud. All right, are you ready? Let's do it. Into the balloons and let them expand. Another experiment you can try is to create your own caps with glowing beads. We have a UV light. Please come and help yourself. We have those beads that if you make a bracelet out of it and radiate with UV light, they will stay colored.